Introduction: the universe's ultimate speed limit. We're about to explore something that sounds deceptively simple, but is actually one of the most mind-bending concepts in all of physics: the speed of light. You've probably heard the number before: 186,282 miles per second, merely some number Einstein happened to use in his equations. It's a cosmic speed limit literally woven into the fabric of space-time itself, an absolute barrier that nothing with mass can ever cross. The consequences of this speed limit are so profoundly strange, so deeply counterintuitive, that they challenge our basic ability to comprehend the universe we inhabit. They force us to abandon nearly all our everyday intuitions about how time, space, and motion work. This is the story of a single number that took humanity 4 centuries to measure accurately. Once we finally succeeded, it shattered everything we thought we knew about time, space, causality, and the fundamental nature of existence itself. By the end of this journey, you'll understand why time genuinely slows down for moving objects, not appears to slow down, but actually runs at a different rate. You'll comprehend why space itself physically contracts in the direction of motion. You'll grasp why 2 observers can disagree about whether events happen at the same moment, and both be completely objectively correct. And you'll see why no matter how advanced our technology becomes, we may never be able to visit even our nearest stellar neighbors within a human lifetime.
The ancient debate: instantaneous or finite? For most of human history, people naturally assumed light traveled instantaneously, that it simply appeared wherever it needed to be with no travel time whatsoever. This assumption makes perfect sense based on everyday experience. When you flip a light switch, the room illuminates immediately with no perceptible delay. When lightning strikes across a valley, you see the flash the instant it occurs, though thunder takes noticeable time to reach you, because sound travels much more slowly. So it seemed obvious, almost self-evident, that light must travel infinitely fast. It just arrives, instantaneously, wherever it's going. The ancient Greek philosopher Empedocles, who lived around 490 to 430 BCE, was one of the first recorded thinkers to question this assumption. He proposed that light was something in motion, something that traveled from place to place, and therefore must take time to make the journey. This was remarkably insightful intuition for someone living 2,400 years ago. But Empedocles' contemporary, Aristotle, dismissed this idea entirely. Aristotle argued with characteristic confidence that light propagation was instantaneous, that light didn't travel at all, but simply appeared wherever it was needed. And because Aristotle's intellectual authority dominated Western thought for over 2 millennia, his view became accepted dogma. If Aristotle said light was instantaneous, then light was instantaneous. Case closed, no further investigation needed. In the Islamic world during the European Middle Ages, the brilliant scholar Al-Hasan ibn al-Haytham, known in the West as Al-Hazen, made significant progress. In his monumental 1021 work, Book of Optics, he proposed that light takes time to travel from one place to another and moves at different speeds through different materials. This was remarkably prescient. He was absolutely correct. But without any way to actually test this hypothesis experimentally, without any means to measure these speeds, his insight remained educated speculation rather than established science. You can have the right answer, but without evidence and experimental verification, it remains just a good guess.
Galileo's failed experiment, the first attempt. The first person to actually attempt measuring light speed experimentally was Galileo Galilei, one of history's greatest scientists. In his 1638 book, 2 New Sciences, Galileo described an experiment that sounds almost comically simple by modern standards. The procedure was straightforward. 2 observers would stand on distant hilltops near Florence, each holding a covered lantern. The first observer would uncover their lantern, sending a flash of light towards the second observer. The moment the second observer saw that flash, they would immediately uncover their own lantern, sending a return signal. By measuring the time interval between uncovering the first lantern and seeing the return flash, Galileo hoped to calculate how long light took to travel the round-trip distance. Galileo attempted this experiment at distances of less than a mile. He detected absolutely no delay whatsoever. The return signal appeared instantaneous. He correctly concluded that light must be, if not instantaneous, then extraordinarily rapid, far faster than anything he could measure with the technology available.
Here's why the experiment was doomed to fail from the start. Light travels approximately 1 mile in about 5.4 microseconds. That's 5.4 millionths of a second, an almost incomprehensibly brief interval. Human reaction time, however, averages around 200 milliseconds, or 200,000 microseconds. Think carefully about what this means. The delay Galileo was trying to measure was roughly 37,000 times smaller than the measurement error introduced purely by human reflexes and the time it takes to consciously react and uncover a lantern. It was like trying to measure the weight of a single grain of sand using a bathroom scale, or timing a bullet's flight with an hourglass. The tool simply wasn't sensitive enough, not even remotely close, for the measurement being attempted. The Accademia del Cimento repeated Galileo's experiment in 1667 with exactly the same null result. It became clear that measuring light speed would require something fundamentally different from human reflexes. It would require looking at much vaster distances. It would require astronomical scales.
Jupiter's moons reveal the truth. The breakthrough came from an entirely unexpected source, the predictable eclipses of Jupiter's moons. Ole Rømer was a Danish astronomer born on September 25, 1644. In the 1670s, he was working at the prestigious Paris Observatory under the famous astronomer Giovanni Domenico Cassini, one of the leading scientists of his era. Rømer's assigned task was to create precise tables predicting when Jupiter's innermost large moon, Io, would disappear behind Jupiter as seen from Earth. These events, called eclipses or occultations, happened with remarkable clockwork regularity. Io orbits Jupiter every 1.769 days, so eclipses occurred predictably and frequently. Accurate predictions of these eclipses were valuable for navigation. Sailors could use them to help determine their longitude at sea, a notoriously difficult problem in that era. But as Rømer compiled his observations carefully over months and years, he noticed something deeply strange and unexpected. The eclipses weren't happening exactly when his mathematical predictions said they should. When Earth was moving toward Jupiter in its orbit around the Sun, the eclipses seemed to occur slightly early, arriving ahead of the predicted schedule. When Earth was moving away from Jupiter, they occurred slightly late, lagging behind predictions.
Over the course of a full year, as Earth completed its orbit, these timing differences accumulated into a significant and undeniable discrepancy of about 22 minutes total.
Rømer realized there was only one explanation that made sense, one way to account for this pattern. Light must take time to travel across space. When Earth was closer to Jupiter in its orbit, there was less distance for the light to cross, so observers on Earth would see the eclipses sooner. They would appear to happen early. When Earth was farther away, the light had to travel a greater distance, causing noticeable delays. The eclipses would appear to happen late. Over the course of a full year, as Earth completed its orbit, these timing differences accumulated into a significant and undeniable discrepancy of about 22 minutes total. Rømer realized there was only one explanation that made sense, one way to account for this pattern. Light must take time to travel across space. When Earth was closer to Jupiter in its orbit, there was less distance for the light to cross, so observers on Earth would see the eclipses sooner. They would appear to happen early. When Earth was farther away, the light had to travel a greater distance, causing noticeable delays. The eclipses would appear to happen late.
The eclipses themselves were happening with perfect regularity, exactly as predicted by orbital mechanics. But the light carrying information about those eclipses to Earth had to cross different distances, depending on where Earth happened to be in its orbit at any given time. Think about what Rømer was realizing, the profound insight he was achieving. He wasn't seeing the eclipses as they actually happened in real time. He was seeing them after a delay that depended on distance. It was similar to watching fireworks from across a valley and noticing that the sound arrives noticeably later than the flash. Except here, even the flash itself was delayed. The light itself needed time to cross the vast gulf of space separating Earth from Jupiter.
On August 22, 1676, Cassini announced to the French Academy of Sciences that future eclipse predictions would need to incorporate corrections for light travel time. Then, in September of that same year, Rømer made an audacious, testable prediction. He calculated that the eclipse of Io, scheduled for November 9th, would occur approximately 10 minutes later than the standard astronomical tables predicted. Think about how bold this was, how much Rømer was risking professionally. He was essentially declaring, "I know when this eclipse will actually be observed, better than the official predictions based purely on orbital mechanics. And the reason is that light takes time to travel." If he was wrong, he would look foolish in front of the entire scientific establishment. If he was right, he would have proven something fundamental about the nature of light itself and revolutionized astronomy. On November 9th, 1676, astronomers across Europe watched and waited with great anticipation. The eclipse occurred at 5:35 and 45 seconds in the morning, exactly 10 minutes late, precisely as Rømer had predicted. It was a triumph of careful observation and brilliant deduction. On November 21st, 1676, Rømer presented his complete findings to the French Academy of Sciences. On December 7th, his work was published in the Journal des Savants. This was the first successful measurement of the speed of light in human history, the first experimental proof that light had a finite speed. Rømer estimated that light takes approximately 22 minutes to cross the diameter of Earth's orbit around the Sun. Using the best estimates of Earth's orbital size available at the time, this gave him a speed of roughly 140,000 miles per second. He was off by about 24–25%, mainly because astronomers in that era didn't yet know the precise size of Earth's orbit. They had the right method, but insufficient data about
astronomical distances. But the critical point is that he had proven what Aristotle got wrong. Light doesn't arrive instantly. It races across space unimaginably fast, faster than anything humans had ever encountered. But it still takes measurable time to get where it's going. Light has a speed, and that speed is finite. Bradley's confirmation, stellar aberration. It would take 53 years for independent confirmation. 53 years before someone else proved Rømer right through a completely different method, approaching the problem from an entirely different angle. In 1728, English astronomer James Bradley discovered something called stellar aberration while searching for an entirely different phenomenon. Bradley was attempting to detect the slight shift in star positions caused by Earth orbiting the Sun, an effect called stellar parallax. This parallax was important because it would provide direct observational evidence that Earth actually orbited the Sun, something that was widely accepted by then, but still hadn't been proven through direct measurement. What Bradley found instead was that stars appeared to shift position by about 20 arcseconds over the course of a year, but in the wrong direction and wrong timing to be parallax. The stars seemed to be displaced in the direction Earth was moving at any given moment in its orbit. This was puzzling. It didn't match any known phenomenon. The explanation came, according to legend, while Bradley was sailing on the Thames River. He noticed that the wind vane on his boat appeared to change direction when the boat changed course, even though the actual wind direction remained constant. The apparent wind direction depended on the boat's motion. He realized starlight behaves the same way. It appears displaced in the direction of Earth's motion. Picture walking through a snowstorm. Even if the snow is falling straight down, you need to tilt your umbrella forward to stay dry because you're moving into the falling snow. Your motion makes the snow appear to come at an angle. Starlight behaves identically. Because Earth is moving through space at about 30 kilometers per second in its orbit, and because light takes time to travel, starlight appears slightly displaced in the direction of Earth's orbital motion. This phenomenon, stellar aberration, only makes sense if light takes time to travel. If light arrived instantly, there would be no aberration effect at all. The fact that aberration exists and has a specific, measurable angle allowed Bradley to calculate light's velocity with impressive accuracy. By measuring the displacement angle and knowing Earth's orbital speed, Bradley calculated light's velocity at between 183,000 and 187,000 miles per second. He was within about 2% of the modern value. More importantly, he had independently confirmed through an entirely different method what Rømer had discovered half a century earlier. Light has a definite, finite, measurable speed. Fizeau's terrestrial measurement, bringing light down to Earth.
the next major advance came from attempting to measure light's speed here on Earth without relying on the vast distances of astronomical space. This was the challenge that had defeated Galileo. How do you measure something that travels a mile in just over 5 microseconds, using equipment you can set up in your local area? Armand Hippolyte Louis Fizeau was a French physicist born on September 23, 1819. On July 23, 1849, he performed an elegant and ingenious experiment, announcing his results to the Académie des Sciences in Paris.
Fizeau set up a bright light source on a bell tower in Cernez, a suburb west of Paris. About 8.6 kilometers away, roughly 5.4 miles, on Montmartre-Clil, he placed a mirror. Between the light source and the distant mirror, he positioned a toothed wheel with 720 teeth arranged around its circumference. Here's how it worked, and it's genuinely clever. Light from the source passed between 2 teeth of the spinning wheel, traveled the 8.6 kilometers to the distant mirror, bounced back, and returned to the wheel. If the wheel wasn't spinning or was spinning slowly, the returning light would pass back through the same gap between teeth and reach the observer's eye. The apparatus would appear bright.
But if the wheel was spinning at just the right speed, something interesting would happen. By the time the light made the round trip of about 17 kilometers, the wheel would have rotated enough that a tooth would now block the path where the gap had been. The light would be cut off. The apparatus would appear dark. By carefully adjusting the wheel's rotation speed, Fizeau could find the exact speed where returning light was blocked, and then the speed where it passed through the next gap. He found that at 25.2 rotations per second, the returning light passed through the next gap over from where it started.
From this measurement, knowing the wheel's rotation speed, the number of teeth, and the total distance light traveled, he could calculate light's velocity. His result was approximately 194,600 miles per second, or about 313,000 kilometers per second. This was about 4.5% too high compared to the modern value, but it was nonetheless a triumph. For the first time in history, light speed had been measured without relying on the vast distances of the solar system. The cosmic could be measured in a laboratory setting. Galileo's dream had finally been achieved, 2 centuries after he first proposed it.
Foucault's refinement, the rotating mirror. Fizeau's former collaborator and rival, Léon Foucault, the same physicist famous for his pendulum demonstrating Earth's rotation, developed an even more refined technique using rotating mirrors instead of toothed wheels. In 1862, Foucault measured light speed at approximately 185,000 miles per second, or about 298,000 kilometers per second. This was only 0.6% different from the modern accepted value, remarkably precise for equipment built over 160 years ago using 19th century technology. But Foucault had accomplished something even more significant 12 years earlier. On April 27, 1850, he demonstrated conclusively that light travels slower in water than in air. This might seem like a minor technical detail, but it was actually decisive evidence in one of physics' longest-running debates.
Isaac Newton had proposed that light consisted of tiny particles, which he called corpuscles. According to Newton's particle theory, light should travel faster in denser materials, like water, because the particles would be attracted and accelerated by the denser medium, pulled in and sped up. The competing wave theory, championed by Christian Huygens and later Thomas Young, predicted exactly the opposite. Light waves should slow down in denser media, just as sound waves behave differently in different materials, traveling faster in dense materials, but through different mechanisms than Newton proposed.
Foucault's 1850 experiment showed conclusively and unambiguously that light travels slower in water than in air, exactly as the wave theory predicted, and opposite to Newton's particle theory. As one historian of physics later put it, this result drove the last nail in the coffin of Newton's corpuscular theory of light. Light behaved as a wave, at least in this crucial test. Newton, for all his towering genius, had gotten this particular question wrong. Even the greatest minds in history can be mistaken, a valuable lesson for all of science.
The precision obsession. The quest for ever greater precision led to Albert Abraham Michelson, an American physicist born on December 19, 1852, in what is now Poland but was then Prussia. Michelson's family immigrated to the United States when he was just 2 years old. At age 17, he received an appointment to the United States Naval Academy directly from President Ulysses S. Grant, an extraordinary achievement. Michelson became genuinely obsessed with precision measurement. His entire scientific career was devoted to measuring things more accurately than anyone had before. In 1878 and 1879, while stationed at the Naval Academy in Annapolis, Maryland, he refined Foucault's rotating mirror technique and obtained a value of approximately 186,350 miles per second. This was the most accurate measurement of light speed in history up to that point, a new benchmark of precision. But Michelson's most famous experiment wasn't actually about measuring how fast light travels. It was about measuring something that, it turned out, didn't exist at all. And this failed experiment would accidentally pave the way for the most revolutionary theory in the history of physics. The luminiferous ether, a ghost in the machine. In the late 19th century, physicists firmly believed that light waves, like all other known waves, needed a medium to travel through. Sound waves require air, water, or some physical substance to propagate. You cannot hear anything in a vacuum because there's nothing for the sound waves to disturb, nothing to carry the vibrations. So what did light waves propagate through? What carried them across the apparent emptiness of space, from the sun to Earth, across millions of miles of vacuum? Scientists proposed the existence of a substance called the luminiferous ether, an invisible, weightless material that filled all of space and carried light waves the way air carries sound. This ether had to have peculiar, almost contradictory properties. It had to be rigid enough to transmit waves at the enormous speed of light, yet fluid enough not to impede the motion of planets, comets, and other celestial bodies sweeping through it. It had to be everywhere, filling all of space down to the smallest scales, yet completely undetectable by any ordinary means. It was a theoretical necessity, but a very strange one. If the ether existed, and if Earth moved through it as our planet orbited the sun at about 30 kilometers per second, then light should travel at slightly different speeds depending on direction. Light traveling in the direction of Earth's motion through the ether would be swimming upstream, so to speak, against the ether wind, and should arrive slightly slower. Light traveling perpendicular to Earth's motion wouldn't face this resistance. The difference would be small, a tiny fraction of light speed, but with sufficiently sensitive equipment, it should be detectable. This ether had to have peculiar, almost contradictory properties. It had to be rigid enough to transmit waves at the enormous speed of light, yet fluid enough not to impede the motion of planets, comets, and other celestial bodies sweeping through it. It had to be everywhere, filling all of space down to the smallest scales, yet completely undetectable by any ordinary means. It was a theoretical necessity, but a very strange one. If the ether existed, and if Earth moved through it as our planet orbited the sun at about 30 kilometers per second, then light should travel at slightly different speeds depending on direction. Light traveling in the direction of Earth's motion through the ether would be swimming upstream, so to speak, against the ether wind, and should arrive slightly slower. Light traveling perpendicular to Earth's motion wouldn't face this resistance. The difference would be small, a tiny fraction of light speed, but with sufficiently sensitive equipment, it should be detectable. The effective path length was about 11 meters, achieved through a complex arrangement of 16 precisely positioned mirrors. The experiment used monochromatic yellow light from a sodium lamp with a wavelength of approximately 589 nanometers. Based on their meticulous calculations, assuming the ether existed and Earth moved through it at orbital speed, they expected to see a fringe shift of approximately 0.4 fringes as they rotated the apparatus to different orientations throughout the day and year. This would provide clear, unambiguous evidence of Earth's motion through the ether and confirm the ether's existence. From April through July of 1887, with key observations made on July 8th, 9th, and 11th, Michelson and Morley conducted their measurements with painstaking care, rotating their apparatus at different times of day, checking and rechecking their results. The result was essentially nothing, 0 with an experimental error. The measured displacement was less than 1/40th of what they expected. It was far too small to indicate any ether wind whatsoever.
The crisis in physics. For his precision optical instruments and the investigations they enabled, Michelson received the Nobel Prize in Physics in December 1907. He was the first American to win the Nobel Prize in any science, a tremendous honor. But the Michelson-Morley experiment had raised a profound puzzle that physics couldn't solve. If there was no ether, what carried light waves through empty space? And why didn't Earth's motion through space affect light's speed? Every other wave we knew about, sound, water waves, waves on strings, had a speed relative to its medium. Light seemed to have an absolute speed, the same for all observers, regardless of their motion. Various physicists proposed solutions. Hendrik Lorentz and George Fitzgerald independently suggested that objects actually contract in the direction of motion through the ether by just the right amount to make the null result come out. This length contraction was a real physical effect in their view, caused by electromagnetic forces compressing matter as it moved through the ether.
But these were ad hoc fixes, adjustments made specifically to save the ether theory, rather than arising naturally from first principles. The physics community was in crisis. The answer would require completely rethinking our understanding of space, time, and motion. It would require a revolution. Interestingly, during the intense preparation for this experiment in September 1885, Michelson suffered a mental breakdown from the pressure and stress. His collaborator, Morley, attributed it to the overwhelming importance of what they were attempting and the perfectionism Michelson demanded. He recovered by October 1885, but the episode shows how much was riding on these measurements, how desperately physicists wanted to understand the fundamental nature of light.
Einstein's miracle year, 1905. In 1905, a 26-year-old man working at the Swiss Patent Office in Bern published 4 papers that fundamentally transformed physics. His name was Albert Einstein, and he had no university position, severely limited access to scientific reference materials and academic journals, and no laboratory whatsoever. He called the patent office his secular monastery, where I hatched my most beautiful ideas. Einstein's main intellectual companion during this period was a colleague named Michele Besso. Einstein later wrote that he could not have found a better sounding board for my ideas in all of Europe. They would walk home together after work, discussing physics, debating concepts, working through problems that had puzzled the greatest minds of the age. From these conversations, some of the most important insights in scientific history emerged. The year 1905 is known as Einstein's Annus Mirabilis, his miracle year. The 4 papers he published in the German journal Annalen der Physik addressed completely different topics, and any single one would have secured his place in scientific history forever. The first paper, received on March 18th and published on June 9th, explained the photoelectric effect and proposed that light comes in discrete packets of energy, which we now call photons. This work would eventually win Einstein the Nobel Prize in 1921, though the committee was reluctant to recognize relativity. The second paper, received on May 11th and published on July 18th, provided mathematical proof that atoms exist by explaining Brownian motion, the random jittering of tiny particles suspended in liquid. This convinced the remaining skeptics that atoms were real physical objects, not just convenient fictions.
The third paper, received on June 30 and published on September 26th, was titled On the Electrodynamics of Moving Bodies, in German, Zur Elektrodynamik bewegter Körper. This 31-page paper introduced the special theory of relativity. It would eventually overturn our understanding of space, time, motion, and causality itself. The fourth paper, received on September 27 and published on November 21st, was just 3 pages long, but contained perhaps the most famous equation in all of science, E equals mc squared. In it, Einstein showed that mass and energy are equivalent, related by the speed of light squared.
Think about what Einstein accomplished in that single year. He was 26 years old,
He had no academic position, no laboratory, no research assistants, no graduate students. He worked 6 days a week examining patent applications for inventions and electrical devices. And in his spare time, during evenings and weekends, he rewrote the foundations of physics. 4 revolutionary papers in a single year. Any one of them would have made him famous. Together, they made him immortal.
The thought experiment, chasing a light beam. Let's focus on that third paper, the one on special relativity, because it's the one that explains why the speed of light fundamentally breaks our everyday understanding of reality.
Einstein had been troubled by a thought experiment since he was about 16 years old, around 1895 or 1896. He described it decades later in his autobiographical notes written in 1946. A paradox upon which I had already hit at the age of 16. If I pursue a beam of light with the velocity c, I should observe such a beam of light as an electromagnetic field at rest, though spatially oscillating. There seems to be no such thing, however, neither on the basis of experience nor according to Maxwell's equations. Think about what teenage Einstein was imagining. Picture yourself running alongside a beam of light, matching its speed exactly, looking over at the light to see what it would look like. According to Newton's physics, which everyone accepted as obviously true, you should see a frozen wave, a stationary ripple in the electromagnetic field, just sitting there next to you as you both traveled together through space.
But James Clerk Maxwell's equations, which described electromagnetism with remarkable accuracy and predicted electromagnetic waves traveling at light speed, didn't allow for such a thing. Maxwell's equations demanded that electromagnetic waves, including light, must always travel at a specific speed, the speed of light. Frozen light, stationary light, light moving at any speed other than the speed of light, simply wasn't physically possible according to these equations.
This paradox nagged at Einstein for years, a full decade of wondering, thinking, turning the problem over in his mind from every conceivable angle. The solution he eventually reached was radical, almost unthinkable. Maybe the premise was wrong. Maybe it wasn't possible to catch up to a beam of light at all. Maybe light always travels at the same speed relative to any observer, no matter how fast that observer is moving.
The 2 postulates, rebuilding physics from scratch. Einstein built his special theory of relativity on 2 fundamental assumptions, or postulates, bedrock principles he took as given.
The first postulate, which he called the principle of relativity, states that the laws of physics are the same in all inertial reference frames. An inertial reference frame is simply a viewpoint that isn't accelerating, moving at constant velocity or at rest. If you're on a smoothly moving train with the windows covered, no experiment you perform inside the train can tell you whether you're moving or stationary. All motion is relative. There's no absolute state of rest, no privileged reference frame, no cosmic background against which motion can be measured absolutely. There's only motion relative to other objects. The 2 postulates, rebuilding physics from scratch. Einstein built his special theory of relativity on 2 fundamental assumptions, or postulates, bedrock principles he took as given. The first postulate, which he called the principle of relativity, states that the laws of physics are the same in all inertial reference frames. An inertial reference frame is simply a viewpoint that isn't accelerating, moving at constant velocity or at rest. If you're on a smoothly moving train with the windows covered, no experiment you perform inside the train can tell you whether you're moving or stationary. All motion is relative. There's no absolute state of rest, no privileged reference frame, no cosmic background against which motion can be measured absolutely. There's only motion relative to other objects.
This principle wasn't new. Galileo had expressed essentially the same idea centuries earlier. It was well accepted by physicists. The second postulate was the revolutionary one. Light always propagates in empty space at the same definite velocity, regardless of the motion of the light source or the motion of the observer. Whether you're moving toward a light source or away from it, whether the source is moving toward you or away from you, whether you're stationary or moving at 99% of light speed,
you will always invariably measure light traveling at exactly the same speed, 299,792,458 meters per second.
These two postulates seem almost reasonable when stated individually. The first one had been around since Galileo. The second one was essentially what the Michelson-Morley experiment had shown. Light's speed doesn't depend on the motion of the source or observer. But together, these two simple assumptions have consequences that violate everything we think we know about how the world works, about how time flows and space extends. The mathematics of special relativity follows inevitably from these two postulates. Everything strange about relativity, time dilation, length contraction, the relativity of simultaneity, mass-energy equivalence, flows inescapably from these two starting points.
Time dilation. Moving clocks run slow. The first major consequence of Einstein's theory is time dilation. When an object moves relative to you, its clock runs slower than yours. Not appears to run slower, actually, genuinely runs slower. Let me emphasize this because it's crucial. A moving clock ticks more slowly than a stationary clock. This isn't an optical illusion. It isn't a mechanical problem with clocks. It isn't a measurement error. Time itself passes more slowly for moving objects.
The mathematical formula involves something called the Lorentz factor, named after Dutch physicist Hendrik Lorentz, who worked out many of these equations before Einstein, but didn't fully understand their implications. Lorentz thought he was describing how objects physically contracted as they moved through the ether. Einstein realized there was no ether, and the equations described something far more fundamental, the nature of spacetime itself. The Lorentz factor depends on how fast something is moving as a fraction of the speed of light. At everyday speeds, walking, driving, even flying in jets, it's essentially equal to 1, meaning time passes normally. But as speeds approach the speed of light, the Lorentz factor grows dramatically, approaching infinity as velocity approaches light speed.
Let me give you concrete numbers so you can truly feel what this means. At 50% of light speed, about 150,000 kilometers per second, the Lorentz factor is approximately 1.155. For every year that passes on Earth, only about 10.4 months pass for someone traveling at that speed. The difference is noticeable but not dramatic. At 90% of light speed, the Lorentz factor jumps to about 2.29. 1 year on Earth corresponds to less than 5.3 months for the traveler. Now we're seeing significant time differences, more than twice as much time passing on Earth. At 99% of light speed, the factor is about 7.09. 1 year on Earth equals only about 51.5 days for someone moving that fast. More than 7 years of Earth time compressed into a single year for the traveler. At 99.99% of light speed, the Lorentz factor is roughly 70.7. For every year passing on Earth, someone traveling at this speed experiences only about 5.2 days, an entire Earth year compressed into less than a week. At 99.99999% of light speed, 6 nines, the factor is approximately 707. For every year on Earth, the traveler experiences only about 12.4 hours, barely half a day. This isn't science fiction speculation. This is measured, verified reality, confirmed by countless experiments over the past century. GPS satellites, particle accelerators, cosmic ray observations, all confirm that time dilation is absolutely real. Length contraction. Space itself shrinks. The second major consequence is length contraction. Objects moving relative to you are physically shorter in the direction of their motion, not visually distorted, actually occupying less space. This isn't some optical illusion caused by light travel time. The object genuinely, physically, measurably occupies less distance along its direction of motion. The formula for length contraction is the inverse of time dilation. At 50% of light speed, an object contracts to about 86.6% of its rest length, noticeably shorter, but not dramatically so. At 87% of light speed, it contracts to exactly half its rest length. At 99% of light speed, it compresses to about 14.1% of its original length. At 99.99%, it's squeezed down to about 1.4%. Consider the Stanford Linear Accelerator in California, a straight tube about 3.2 kilometers, 2 miles long. Inside this tunnel, electrons are accelerated to 99.99999999% of the speed of light, so close that the difference is almost impossible to express. From the electron's perspective, because of length contraction, the entire accelerator appears to be only about 6 centimeters long, roughly 2 inches. The electrons experience themselves as passing through a tunnel shorter than your handspan, even though, from our perspective, the tunnel stretches for 2 miles. This is genuine physical reality. The electrons truly experience a shorter distance. From their reference frame, the tunnel really is only 2 inches long. The universe doesn't privilege one viewpoint over another. Both perspectives are equally valid, equally real. The relativity of simultaneity. No universal now. The third consequence may be the strangest and most philosophically disturbing of all, the relativity of simultaneity. Events that happen at the same time for one observer may not happen at the same time for another observer moving relative to the first. There is no universal absolute now that all observers agree on. Einstein illustrated this with a thought experiment involving a train and lightning strikes. Imagine lightning strikes both ends of a moving train at exactly the same instant from the perspective of someone standing on the platform beside the tracks. That stationary observer sees both flashes simultaneously because the light from each strike has to travel the same distance to reach their eyes. But what about someone sitting in the exact middle of the train? The train is moving forward. The light from the front strike has a shorter distance to travel because the observer is moving toward where that strike occurred. The light from the rear strike has a longer distance to travel because the observer is moving away from where that strike occurred. Light travels at the same speed for all observers, so the passenger on the train sees the front strike first, then the rear strike. You might object, that's just light travel time. The strikes really were simultaneous. The passenger is just seeing them at different times because of how long the light took to arrive. But here's the revolutionary insight. In special relativity, there is no way to determine which observer is really correct about whether the strikes were simultaneous. Neither perspective is privileged. The universe doesn't have a master clock that everyone agrees on. For the platform observer, the strikes are genuinely simultaneous. For the train passenger, they genuinely occur at different times. Both are correct from their reference frames.
E equals mc squared, mass and energy united. The fourth paper Einstein published in 1905 dealt with the relationship between mass and energy. It carried the understated title, "Does the inertia of a body depend upon its energy content?" In just 3 pages, Einstein demonstrated that mass and energy are 2 forms of the same fundamental thing. The famous equation E equals mc squared didn't actually appear in that exact form in the original paper. Einstein wrote it differently, using L for energy, from the German word Leistung, and V for velocity. But the meaning was the same. Energy equals mass times the speed of light squared. The implications are staggering beyond comprehension. Mass can be converted entirely into energy. Energy can be converted entirely into mass. And because the speed of light squared is such an enormous number, approximately 9 times 10 to the 16th in SI units, a tiny amount of mass contains an almost inconceivable amount of energy. Think about what this means concretely. 1 kilogram of matter, if completely converted to pure energy, would release about 90 quadrillion joules, roughly equivalent to a 21 megaton nuclear explosion. The mass of a single paperclip, completely converted, could power a medium-sized city for days.
This equation explains why the sun shines. Deep in the sun's core, at temperatures of 15 million degrees Celsius, hydrogen nuclei fuse together to form helium through nuclear fusion. 4 hydrogen nuclei combine to make 1 helium nucleus, but the helium weighs slightly less than the original hydrogen, about 0.7% less mass. Where does that missing mass go? It becomes energy, radiating outward as the sunlight that warms our planet and makes life possible.
the sun is slowly converting its mass into energy at a rate of about 4 million tons every single second. It's been doing this for 4.6 billion years and will continue for another 5 billion years before exhausting its fuel. The equation also explains nuclear weapons and nuclear power. When heavy atoms like uranium or plutonium split apart and fission, or when light atoms like hydrogen fuse together in fusion, a tiny fraction of their mass converts to energy according to E equals mc squared. The atomic bomb dropped on Hiroshima converted less than 1 gram of matter into energy, less than the mass of a paperclip, and that was enough to destroy an entire city and kill over 100,000 people, making the impossible real. Everything we've discussed might sound like elaborate theoretical speculation, beautiful mathematics divorced from reality. How do we know any of this is actually true? How do we know time really slows down, space really contracts, that E equals mc squared isn't just an elegant equation, but actual truth? The answer is we've tested these predictions repeatedly with exquisite precision, and Einstein's predictions have been confirmed absolutely every single time, without exception. The most dramatic direct test was the Hafele-Keating experiment. In October 1971, physicists Joseph Hafele of Washington University in St. Louis and Richard Keating of the United States Naval Observatory decided to test the twin paradox with actual atomic clocks flown around the world on commercial airlines. They purchased seats on commercial flights and took 4 cesium beam atomic clocks, the most precise timepieces available, around the world twice, once eastward and once westward. The eastward trip departed on October 4, 1971, covering 65.4 hours total. The westward trip occurred on October 13, lasting 80.3 hours. Why both directions? Because special relativity, velocity effects, and general relativity, gravitational effects, had to be separated. Flying eastward, the planes moved in the same direction as Earth's rotation, increasing their velocity relative to Earth's center. Flying westward, they moved against Earth's rotation, decreasing their effective speed. Additionally, at cruising altitude of about 10 kilometers, the clocks experienced slightly weaker gravity than clocks on the ground, which affects time through general relativity.
Einstein's theories predicted specific time differences. The eastward traveling clocks should lose about 40 nanoseconds relative to ground clocks. The westward traveling clocks should gain about 275 nanoseconds. The results, published in Science magazine in 1972, confirmed Einstein's predictions with remarkable accuracy. The eastward clocks lost 59 nanoseconds, plus or minus 10. The westward clocks gained 273 nanoseconds, plus or minus 7. Both results fell squarely within predicted ranges. These are tiny time differences, less than a millionth of a second, but they were exactly what relativity predicted, down to the limits of measurement precision. The twin paradox isn't just a thought experiment, it's measurable reality. The experiment cost only about $8,000, mostly for purchasing airline tickets. The atomic clocks were given their own passenger seats, and tickets were purchased for them under the name Mr. Clock. It remains one of the most inexpensive yet definitive tests of fundamental physics ever conducted. Perhaps the most practical, everyday confirmation of relativity is the global positioning system. The GPS in your phone, car, or watch wouldn't work without relativistic corrections built into the system. Every time you use GPS to navigate, you're relying on Einstein's relativity to function correctly. GPS works by measuring the time for radio signals to travel from satellites to your receiver. Each GPS satellite carries atomic clocks, accurate to about 1 nanosecond. By comparing signals from multiple satellites, the receiver can triangulate your position to within a few meters. But there's a problem that would be catastrophic without relativity. The satellites orbit at about 20,200 kilometers altitude, traveling at roughly 14,000 kilometers per hour. Special relativity predicts their clocks should run slower than ground clocks by about 7 microseconds per day because of their velocity. However, at that altitude, gravity is weaker than at Earth's surface. General relativity predicts that clocks in weaker gravity fields run faster. they should gain about 45 microseconds per day compared to ground clocks. The net result? Satellite clocks run about 38 microseconds per day faster than ground clocks. That might not sound like much, but light travels about 11.4 kilometers in 38 microseconds. Without relativistic corrections, GPS positioning errors would accumulate at a rate of over 11 kilometers per day. Within just 2 minutes, the system would be completely useless for navigation.
The solution is elegant. GPS satellite atomic clocks are manufactured to tick at a slightly different frequency than ground clocks, 10.22999954 MHz instead of the standard 10.23 MHz. This pre-compensates for the relativistic time difference, keeping the system synchronized and accurate. Every time you use GPS to navigate to a destination, find a restaurant, or track your morning run, you're relying on Einstein's relativity. If relativity were wrong, GPS simply wouldn't work. The fact that it does work precisely and reliably every single day for billions of people is powerful confirmation that relativity describes reality accurately.
An even more dramatic natural demonstration happens constantly in Earth's atmosphere. Cosmic rays, high-energy particles from space, constantly bombard the upper atmosphere, creating secondary particles called muons at altitudes around 10 kilometers. Muons are subatomic particles similar to electrons, but about 200 times heavier. They're unstable, decaying into other particles with a half-life of 2.2 microseconds when measured at rest in a laboratory. That's 2.2 millionths of a second, barely any time at all. Here's the problem. Even traveling at the speed of light, in 2.2 microseconds, a muon can only travel about 660 meters before half of them decay. Starting from 10 kilometers altitude, essentially none should reach Earth's surface. They simply don't have enough time before decaying.
But they do reach the surface in large numbers. We detect cosmic ray muons constantly at sea level. Physicists first noticed this discrepancy in the 1930s and 1940s. The muons seem to be living much longer than they should. The explanation is time dilation. The muons are traveling at approximately 99.8% of the speed of light. From our perspective on the ground, their internal clocks are running slow by a factor of about 15. Their 2.2 microsecond lifetime stretches to approximately 33 microseconds from our viewpoint, giving them plenty of time to reach the surface.
From the muons' perspective, the explanation is different but completely equivalent. They're not living longer than 2.2 microseconds by their own clocks, but from their viewpoint, Earth's atmosphere is length contracted. The 10 kilometers they need to cross appears as only about 650 meters due to relativistic contraction. They easily make the journey within their allotted lifetime. Two completely different explanations: time dilation from our frame, length contraction from theirs, both giving exactly the same answer, both equally valid. This is the beauty and consistency of relativity. From the muons' perspective, the explanation is different but completely equivalent. They're not living longer than 2.2 microseconds by their own clocks, but from their viewpoint, Earth's atmosphere is length contracted. The 10 kilometers they need to cross appears as only about 650 meters due to relativistic contraction. They easily make the journey within their allotted lifetime. Two completely different explanations: time dilation from our frame, length contraction from theirs, both giving exactly the same answer, both equally valid. This is the beauty and consistency of relativity.
Think of it like accelerating a car that gets heavier the faster it goes. At first, pressing the accelerator makes a big difference. But as you approach some maximum speed, each additional kilometer per hour requires exponentially more fuel. The car responds less and less to the same force. Eventually, you're burning infinite fuel just to creep toward a speed you can never quite reach.
For a real object with mass, as it approaches light speed, it becomes effectively infinitely massive, requiring infinite force, infinite energy to accelerate it any further. To reach exactly light speed would require literally infinite energy, an amount that cannot exist in a finite universe. But here's the flip side. Particles without mass must travel at exactly the speed of light. They cannot travel at any other speed. Photons, particles of light, have zero rest mass. They're born moving at light speed and never slow down until they're absorbed by matter.
They cannot move at any speed other than c, because the equations of physics, combined with their zero mass, demand it.
The consequences of special relativity challenge our most basic assumptions about the nature of reality, raising profound philosophical questions that remain debated today. If there is no universal now, if different observers legitimately disagree about what is happening at this moment in distant places, then what does the present moment even mean? What is real? Einstein himself came to embrace what philosophers call the block universe, or eternalism. In this view, past, present, and future all exist equally. Space-time is like a four-dimensional block, with all events at all times existing simultaneously. Our experience of time flowing, of now moving from past to future, is an illusion, a peculiarity of consciousness, not a fundamental feature of physics. Einstein expressed this view movingly after the death of his lifelong friend Michele Besso in 1955. He wrote to Besso's family, "Now he has departed from this strange world a little ahead of me. That means nothing. People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion." Einstein died just weeks after writing this. If his block universe view is correct, then Besso and Einstein both still exist, frozen in the space-time of their lifetimes, as eternally real as any moment we call present. The flow of time in this view is similar to how the landscape changes as you drive down a highway. The highway exists all at once, but your experience moves along it sequentially. We've traced humanity's 4-century quest to measure the speed of light and understand its consequences. From Rømer watching Jupiter's moons to Einstein revolutionizing physics. From Michelson's precision obsession to GPS satellites orbiting overhead, the speed of light has proven to be far more than just a number. It's woven into the fundamental structure of space-time itself. It connects mass and energy through the universe's most famous equation. It defines causality, the maximum speed at which cause and effect can propagate. It determines what we can see, what we can reach, and what remains forever beyond our cosmic horizon. The speed of light isn't arbitrary. It's not something that could be different in another universe while keeping everything else the same. It's built into the fabric of reality in ways we're still discovering. 186,282 miles per second. 299,792,458 meters per second exactly by definition. A number that took centuries to measure, that shattered our understanding of time and space, that revealed the universe to be stranger and more beautiful than anyone imagined. The next time you flip a light switch, remember, those photons illuminating your room are traveling at the universe's ultimate speed limit, the cosmic constant that binds together space, time, matter, and energy into one magnificent, comprehensible, yet ultimately mysterious whole. That's the true meaning of the speed of light. Not just how fast light travels, but what kind of universe we live in. A universe where the distinction between space and time blurs, where motion through space becomes motion through time, where reality itself proves more subtle and strange than everyday experience suggests. And somehow, remarkably, we figured it out. Understanding the speed of light isn't just about celebrating what physics has achieved. It's also about confronting the harsh limitations this cosmic speed limit places on humanity's future among the stars. Consider communication with spacecraft exploring our solar system. The moon is about 384,400 kilometers away. Light takes 1.28 seconds to make the trip, meaning a round-trip communication takes 2.56 seconds. This was manageable during the Apollo missions, though it made real-time conversation awkward. You can hear the pauses in the mission recordings, brief silences where signals cross the void.
Mars presents a much greater challenge. At its closest approach to Earth, during opposition, when both planets align on the same side of the Sun, Mars lies approximately 55 million kilometers away. Light takes about 3 minutes to cross this distance. A round-trip message requires at least 6 minutes. You ask a question, and the earliest you can possibly receive an answer is 6 minutes later. But Mars isn't always that close.
At its farthest, when Mars and Earth are on opposite sides of the Sun, the distance grows to about 401 million kilometers. One-way light travel time stretches to 22 minutes. Round-trip communication takes 44 minutes. You send a command to a Mars rover, and you must wait nearly 3/4 of an hour to see the result, to know whether it worked or failed catastrophically.
This isn't a technology problem we can solve with better radios or more powerful transmitters. It's a fundamental feature of space-time itself. No signal can travel faster than light. Communication delays cannot be eliminated, only planned for. Any crewed mission to Mars must account for this isolation. Astronauts cannot phone home for immediate help. They must be completely self-sufficient, prepared for every contingency, because help is always minutes away at the speed of light. The Voyager 1 spacecraft, launched in 1977, is now over 24 billion kilometers from Earth, about 161 astronomical units. Light takes approximately 22.5 hours to reach Voyager 1. A command sent today won't arrive until tomorrow. A status report sent by Voyager today won't reach Earth until tomorrow. We're conducting a conversation with a delay of nearly 2 days between exchanges.
And Voyager 1 is still within our solar system's outer reaches, barely scratching the edge of interstellar space. The nearest star system, Alpha Centauri, lies 4.24 light-years away, about 40 trillion kilometers. Any message we send would take more than 4 years to arrive. Any reply would take another 4 years to return. A single exchange spans 8.5 years. Maintaining a conversation with beings around another star would be generational. Parents might send questions their children would answer. The cosmic speed limit doesn't just affect communication. It determines what we can see, what we can know about the universe. Because light takes time to travel, looking at distant objects means looking backward in time.
When we observe the sun, we see it as it was 8 minutes and 20 seconds ago. When we look at the nearest star, we see it as it was over 4 years ago. When we observe the Andromeda galaxy, the nearest large galaxy to our own, we see it as it was 2.5 million years ago, when our ancestors were still developing stone tools, when modern humans didn't yet exist. The observable universe has a radius of approximately 46.5 billion light-years. This isn't because the universe is that age. The universe is only 13.8 billion years old. The observable radius is larger because space itself has been expanding. Light that started traveling toward us 13.8 billion years ago, shortly after the Big Bang, has had that time to reach us. But the sources of that light have continued receding as space expands. By now, those sources are about 46.5 billion light-years away.
Beyond that cosmic horizon, light simply hasn't had time to reach us. There may be vastly more universe beyond what we can observe, perhaps infinitely more, but we have no way to know and can never know.
Those regions are fundamentally, permanently beyond our cosmic horizon. Even stranger, galaxies beyond the Hubble radius, roughly 14 billion light-years away, are receding from us faster than light due to the expansion of space itself. This doesn't violate relativity, because special relativity prohibits objects from moving through space faster than light, but says nothing about space itself expanding. These galaxies aren't flying through space at superluminal speeds. Space is stretching between us and them, carrying them away.
Light emitted now from galaxies beyond our Hubble horizon will never reach us. Those regions of the universe are irreversibly beyond our reach, cut off from us forever by the combination of cosmic expansion and the finite speed of light. We are fundamentally isolated from most of the universe.
Exotic possibilities. Can we cheat? Given how restrictive the light speed barrier is, it's natural to ask whether there might be any way around it, any loophole in the laws of physics that might allow faster-than-light travel or communication. Scientists and science fiction writers have explored numerous possibilities. Most turn out to be impossible, but a few remain tantalizingly open questions.
Quantum entanglement is often misunderstood as potentially enabling faster-than-light communication. When two particles become quantum entangled, measuring one instantaneously affects what you'll find when measuring the other, regardless of the distance separating them. Einstein called this spooky action at a distance.
In 2022, the Nobel Prize in Physics was awarded to Elaine Espect, John Clauser, and Anton Zeilinger for experiments with entangled photons that definitively proved quantum entanglement is real, that the correlations Einstein found so troubling genuinely exist in nature. Many people hear about entanglement and think it could enable faster-than-light communication. It cannot, and there's a rigorous mathematical proof called the no-communication theorem that demonstrates why.
First, when you measure an entangled particle, you get a random result from a specific probability distribution. You cannot choose or control what outcome you'll get. The measurement outcome is genuinely random. Second, neither party can tell whether the other has performed a measurement just by looking at their own results. The correlations between entangled particles only become visible when you bring the measurement results together and compare them, which requires normal light speed or slower communication. The spooky action creates perfect correlations between measurement outcomes, but those correlations look completely random to each individual observer until they compare notes. You can't send information using quantum entanglement because you can't control what message the random results spell out. Imagine two friends, Alice and Bob, each with an entangled coin. When Alice flips heads, Bob necessarily flips tails, and vice versa. But neither can control whether they flip heads or tails. The outcome is random for each of them. Alice can't send Bob a message by flipping her coin in specific patterns because she can't determine what result she'll get. Only when they meet later and compare their sequences do they see the perfect anti-correlation. Quantum entanglement works identically, perfect correlation, but no ability to control outcomes or transmit information.
Tachyons are hypothetical particles that would always travel faster than light. In 1967, physicist Gerald Feinberg published a paper exploring this possibility. He coined the term tachyon from the Greek word for swift. Tachyons would have bizarre properties. They would have imaginary mass, meaning their mass squared would be a negative number, a property that seems physically meaningless. They would always travel faster than light, never slower, just as ordinary particles always travel slower than light. Adding energy to a tachyon would slow it down rather than speed it up. They would approach light speed as an upper limit from above, just as we approach it as a lower limit from below. The fundamental problem with tachyons is causality. If tachyons existed and could carry information, they would enable signals to be received before they were sent from certain reference frames. This creates logical paradoxes. You could potentially send a message to yourself in the past, creating scenarios where you prevent yourself from sending the message in the first place. No tachyons have ever been detected, despite decades of searching. Most physicists believe they don't exist and cannot exist without breaking the logical consistency of physics. It's worth noting that tachyonic fields do appear in certain quantum field theory calculations, but these don't represent faster-than-light particles. They're mathematical indicators that a field configuration is unstable, like a ball balanced on top of a hill ready to roll down.
The Alcubierre warp drive is a more interesting possibility from general relativity. In 1994, Mexican physicist Miguel Alcubierre published a paper showing that Einstein's equations permit a configuration of spacetime where a bubble of flat space could move faster than light relative to distant observers. The idea is elegant. Instead of moving through space at superluminal speeds, which special relativity forbids, you would contract space in front of your ship and expand it behind. The ship inside the bubble would be locally stationary, not moving at all relative to nearby space, while the bubble itself moved, carried along by the contraction and expansion of space itself.
This technically doesn't violate special relativity, which prohibits objects from moving through spacetime faster than light, but says nothing about spacetime itself moving. The problem is that creating such a bubble would require what physicists call exotic matter, matter with negative energy density. In ordinary physics, energy density is always positive or zero. Negative energy density would be something unlike any known material, possibly violating energy conditions that most physicists believe must hold.
Initial calculations suggested creating an Alcubierre bubble would require the equivalent of Jupiter's entire mass converted to energy, an impossibly vast amount. In 2011-2012, physicist Harold White at NASA showed that changing the bubble's geometry from a sphere to a toroid could dramatically reduce energy requirements. But dramatically reduced still means far beyond any conceivable technology, perhaps reducing the requirement from impossible to merely absurdly impossible. There are other problems too. How would you steer such a bubble? How would you stop it? Light traveling at the bubble's front couldn't reach the ship inside to provide information about obstacles ahead. The bubble might accumulate extremely high energy particles at its leading edge, releasing them as a devastating radiation blast when the drive disengaged, potentially sterilizing your destination.
Wormholes represent another theoretical possibility. These are solutions to Einstein's equations that connect two distant points in spacetime through a shortcut, a tunnel through the fabric of reality itself. Einstein himself, along with Nathan Rosen, described these solutions in 1935, now called Einstein-Rosen bridges. But the original Einstein-Rosen bridges are non-traversable. They collapse too quickly for anything to pass through. Any object attempting to enter would be crushed before reaching the other end.
In 1988, physicist Kip Thorne and his student Michael Morris explored what it would take to create a traversable wormhole, prompted by a question from Carl Sagan for his novel Contact. They found that stabilizing a wormhole large enough to pass through would require negative energy equivalent to Jupiter's mass, the same impossibly vast requirement as the Alcubierre drive. Moreover, if wormholes could be created and stabilized, they would raise the same causality concerns as any faster-than-light method. If one end of a wormhole is moved at high speed relative to the other, time dilation would cause the two ends to experience different amounts of time. Step through the wormhole at the right moment, and you might emerge in your own past, creating all the logical paradoxes that physicists find so troubling.
There is one way to exceed light speed that's completely real and experimentally verified: traveling faster than light in a medium. Light travels at c equals 299,792,458 meters per second in vacuum. But in other materials, it travels slower because of how light interacts with atoms and molecules. In water, light moves at about 225,000 kilometers per second, roughly 75% of its vacuum speed. In glass, about 200,000 kilometers per second, approximately 67%. In diamond, only about 124,000 kilometers per second, about 41% of vacuum speed.
The ratio of light's vacuum speed to its speed in a medium is called the refractive index. Water has a refractive index of about 1.33. Glass is around 1.5. Diamond is approximately 2.42, which is why diamonds sparkle so brilliantly. The high refractive index bends light sharply at surfaces, creating internal reflections. A charged particle moving through water faster than light moves through water creates an electromagnetic shockwave, similar to a sonic boom. This phenomenon is called Cherenkov radiation, named after Soviet physicist Pavel Cherenkov, who systematically observed it in 1934. He shared the 1958 Nobel Prize with colleagues Igor Tamm and Ilya Frank for explaining the phenomenon.
If you've seen photographs of nuclear reactor cooling pools, you've seen Cherenkov radiation. The water glows an eerie, beautiful blue because electrons from nuclear reactions are traveling faster than light travels in water. These electrons are knocked loose by high-energy gamma rays from the reactor core and zip through water at perhaps 60 or 75% of light's vacuum speed, well below the cosmic limit, but faster than light space in water. This doesn't violate relativity because the fundamental limit is the speed of light in vacuum. Nothing can exceed that absolute barrier, but particles can exceed light speed in a medium while remaining below the vacuum speed.
Behind the equations and experiments are human stories, brilliant minds driven by curiosity, sometimes facing skepticism, always pushing against the boundaries of knowledge. Rømer's prediction in 1676
was initially met with skepticism by many astronomers. The idea that light had a speed seemed counterintuitive. Cassini himself, Rømer's supervisor, later rejected Rømer's interpretation, preferring alternative explanations for the timing discrepancies. It took Bradley's independent confirmation 53 years later for the scientific community to fully accept that light traveled at finite speed. Michelson devoted his entire career to precision measurement with almost obsessive dedication. His biographer wrote that he pursued exactness as other men pursue wealth or glory. The Michelson-Morley experiment's null result was initially disappointing to Michelson. He had hoped to measure Earth's motion through the ether, not prove the ether didn't exist. He never fully appreciated that his failed experiment paved the way for Einstein's revolution.
When Einstein submitted his relativity paper in 1905, he was unknown, a patent clerk with no academic position, no credentials, no reputation. The journal that published it, Annalen der Physik, didn't use peer review in the modern sense. If Einstein had needed approval from established professors, his work might never have seen print. Sometimes revolutionary ideas come from outsiders unburdened by conventional thinking. Max Planck, one of Germany's most respected physicists, was one of the first to recognize Einstein's achievement. Planck's support was crucial for gaining Einstein broader acceptance. Einstein later wrote, "The attention that this theory so quickly received from colleagues is surely to be ascribed in large part to the resoluteness and warmth with which he intervened for this theory." Einstein's Nobel Prize in 1921, awarded in 1922 due to committee delays, notably didn't mention relativity. Committee member Alvar Gullstrand was actively hostile to Einstein's work, allegedly declaring that Einstein must never receive a Nobel Prize, even if the whole world demands it. The compromise was awarding it specifically for the photoelectric effect, proven and uncontroversial, rather than relativity, which some still questioned. At Einstein's Nobel lecture on July 11, 1923, despite officially receiving the prize for the photoelectric effect, he spoke entirely about relativity and never once mentioned the photoelectric effect, a subtle but pointed commentary on the committee's evasion. The story of Arthur Eddington's 1919 eclipse expedition to test general relativity is worth telling. Eddington, a British astronomer, organized expeditions to observe a total solar eclipse and measure whether starlight was bent by the sun's gravity, as Einstein predicted. One team went to Sobral, Brazil, another to Principe, an island off West Africa.
The observations were technically difficult, requiring precise measurements during the brief minutes of totality. When the results came back positive, confirming Einstein's prediction, Eddington became Einstein's champion in the English-speaking world. The announcement made Einstein instantly famous. Newspaper headlines worldwide proclaimed revolution in science and Newton's ideas overthrown. Einstein reportedly reacted to the news with characteristic confidence. When asked what he would have said if the results had contradicted his theory, he shrugged. "Then I would have been sorry for the dear Lord. The theory is correct." He had such faith in the mathematics that experimental confirmation seemed almost superfluous.
Despite more than a century of experimental confirmation, special relativity still raises philosophical questions that lack definitive answers. The block universe view, where past, present, and future all exist equally, seems to follow naturally from relativity. If there's no universal now, if different observers disagree about what's happening at this moment in distant places, then how can we maintain that only the present is real? The logical argument for eternalism appears compelling. Yet, many physicists and philosophers resist this conclusion, finding it incompatible with our direct experience of time's flow, with the apparent difference between fixed past and open future. Various alternatives have been proposed. Presentism, only the present exists. The growing block universe, past and present exist, future doesn't yet. Or accepting that reality is fundamentally perspectival rather than absolute. Another deep question concerns the speed of light itself. Why does it have the particular value it does? Why 299,792,458 meters per second, rather than some other number?
Physics can only answer that it simply is this value. The speed of light is a fundamental constant, not derivable from anything more basic. It appears in equations as a given, not as a consequence of deeper principles. Some physicists have speculated about what the universe would be like with different values of c.
finding that most such universes couldn't support complex structures like atoms, stars, or life. We observe the value we do because we couldn't exist otherwise, an anthropic argument that some find satisfying and others find deeply unsatisfying.
The connection between mass and energy through E=mc² raises its own philosophical puzzles. What does it mean that mass and energy are equivalent? Are they truly the same thing viewed differently? Or are they distinct but interconvertible? The mathematics gives precise predictions, but the ontological status, what it tells us about the fundamental nature of reality, remains debated.
Perhaps most fundamentally, what is space-time? Is it a real physical thing, a substance that can bend and flex? Or is it merely a mathematical framework for describing relationships between events? General relativity treats space-time as dynamic and physical, but quantum mechanics suggests something more subtle might be going on at the smallest scales. These questions remain open, keeping philosophers and physicists busy in coffee shops and conference rooms worldwide.
The legacy, a century of confirmation. More than 120 years after Einstein's miracle year, special relativity remains one of the most thoroughly tested and confirmed theories in all of physics. Every prediction has been verified, often to extraordinary precision. Particle accelerators routinely accelerate particles to speeds where relativistic effects completely dominate. The Large Hadron Collider accelerates protons to 99.9999991% of light speed. At this velocity, the protons have about 7,460 times their rest mass and kinetic energy, exactly as relativity predicts. Time dilation extends their lifetimes by the same factor.
When these protons collide, the energy of collision creates new particles with masses far exceeding the protons' rest masses, energy becoming matter, exactly as E=mc² demands. The Higgs boson, discovered in 2012, has a mass about 133 times a proton's mass, all created from collision energy. Atomic clocks have been tested in countless configurations. Clocks flown on aircraft show exactly predicted time differences. Clocks taken to different altitudes show gravitational time dilation, matching general relativity. GPS satellites require relativistic corrections that work perfectly.
Astrophysical observations confirm relativity on cosmic scales. Binary pulsars, pairs of neutron stars orbiting each other, lose energy through gravitational wave emission at precisely the rate general relativity predicts, causing their orbits to gradually decay. The 1993 Nobel Prize was awarded for these observations, which provided the first indirect evidence for gravitational waves decades before they were detected directly. In 2015, LIGO detected gravitational waves directly for the first time from colliding black holes 1.3 billion light-years away. Since then, dozens more detections have confirmed that gravitational waves propagate at exactly the speed of light, as theory demands.
The cosmic microwave background, radiation from the Big Bang itself, provides tests of relativity on the largest scales. The patterns in CMB temperature fluctuations match predictions from relativity-based cosmological models with extraordinary precision.
Every single test, from subatomic to cosmic scales, confirms Einstein's insights. Relativity isn't just approximately correct or a useful approximation. It's demonstrably accurate to the limits of our measurement precision, which in some cases means parts per trillion or better. Conclusion: the number that contains a universe. We began with a simple question: how fast does light travel? 4 centuries of inquiry, from Galileo's hilltop lanterns to Einstein's thought experiments to GPS satellites orbiting overhead, have revealed that this question opens onto something far deeper than a mere number. The speed of light is 299,792,458 meters per second. Exactly, by definition. This number is now one of the fixed constants defining our system of units. But what it represents is so much more than a measurement.
It's the cosmic speed limit, the maximum rate at which cause can influence effect, the boundary separating what we can know from what remains hidden beyond our cosmic horizon. It's the conversion factor between mass and energy, explaining why stars shine and atoms hold together. It's the coupling constant between space and time, revealing that what we thought were separate things are actually unified into space-time. The speed of light breaks our everyday understanding of reality because everyday experience evolved at walking speeds on a small planet. Our intuitions about time being absolute, space being fixed, simultaneity being universal, these are all approximately correct at human scales, but fundamentally wrong when examined closely.
Einstein showed us that time is relative, space is flexible, simultaneity is observer-dependent, and the past, present, and future might all exist equally in the block of spacetime. These aren't philosophical speculations, but experimental facts, confirmed repeatedly with ever-increasing precision. Every time you use GPS, you're relying on relativity. Every time astronomers observe distant galaxies, they're looking backward in time determined by light. Every time particle physicists collide protons, they're converting energy to matter, according to E equals mc squared. Relativity isn't abstract theory divorced from reality. It's woven into modern technology and modern understanding of the cosmos. The speed of light teaches us that the universe is subtle and strange in ways our ancestors never imagined. But it also teaches us something profound about human capability. We evolved as apes on an African savanna, with brains designed to find food, avoid predators, and navigate social relationships. Nothing in our evolutionary history prepared us to understand relativity, quantum mechanics, or cosmology. Yet we figured it out anyway, through careful observation, rigorous mathematics, and willingness to follow evidence wherever it leads, even to counterintuitive conclusions. We've mapped the architecture of space-time itself. This is humanity at its best, curious, persistent, humble before reality, yet bold in imagination.
The speed of light isn't just a number. It's a window into the deepest structure of existence, a key that unlocks secrets of space, time, matter, and energy. It reveals that we live in a universe far more interesting, more subtle, more beautiful than our everyday experience suggests. And somehow, remarkably, against all odds, we figured it out.
That's the true wonder, not just that the speed of light has these strange properties, but that we, a species of clever apes from a small blue planet, could discover them through thought and experiment, that we could measure the unmeasurable,
Conceive the inconceivable, and understand truths that shatter our intuitions, yet describe reality with stunning accuracy. The next time you see a beam of light, remember, those photons are traveling at the universe's ultimate speed limit, the cosmic constant that binds everything together into one magnificent, comprehensible, yet endlessly mysterious whole. We live in Einstein's universe now, whether we realize it or not. The strange consequences of special relativity aren't just abstract physics. They're the actual structure of reality we inhabit every moment of our lives. Right now, as you read these words, you're moving through time at a slightly different rate than someone traveling in an airplane overhead. The difference is tiny, unmeasurable without atomic clocks, but it's real. Time genuinely passes at different rates for different observers, depending on their motion and position in gravitational fields.
Right now, particles in cosmic rays are living longer than they should because of time dilation, while from their perspective, Earth's atmosphere is contracted to a fraction of its actual thickness. Both viewpoints are equally valid. Reality accommodates both simultaneously without contradiction. Right now, GPS satellites are correcting for relativistic time dilation, adjusting their clocks by 38 microseconds per day to stay synchronized with ground clocks. Without these corrections, navigation would become useless within hours. Einstein's century-old theory is built into the infrastructure of modern civilization.
Right now, somewhere in a particle accelerator, protons are colliding at 99.9999991% of light speed. Their kinetic energy converted into new particles that didn't exist microseconds before. Matter created from energy, according to E equals mc squared. The equation isn't just true, it's useful, practical, the foundation of nuclear medicine and our understanding of how stars shine.
Right now, light from distant galaxies is reaching Earth after journeys spanning millions or billions of years. We're literally looking backward in time every time we gaze at the night sky. The universe reveals its history to us because light has finite speed, because the cosmos is large enough that even light's tremendous speed requires eons to cross it. Understanding these truths doesn't diminish the mystery and wonder of existence. If anything, it deepens them. The universe is stranger than we imagined, but we were clever enough to figure that out. Reality violates our intuitions, but we had the intellectual honesty to change our intuitions rather than deny reality.
The speed of light stands as a monument to human curiosity and capability. For 4 centuries, generation after generation of scientists worked to measure it, understand it, explain it.
Each built on the work of predecessors, adding precision, developing new techniques, asking deeper questions. Rømer watched Jupiter's moons with telescopes barely more sophisticated than Galileo's. Fizeau spun toothed wheels and bounced light across hilltops. Michelson floated interferometers on pools of mercury, obsessing over fractions of wavelengths. Einstein sat in a patent office, thinking about light beams and moving trains, following his thoughts wherever they led, regardless of how strange the destination.
And now we know. Light travels at 299,792,458 meters per second. Not because that's how fast it goes, but because that's how space-time is structured. The speed of light isn't a property of light, it's a property of reality itself, the maximum speed at which causality propagates, the conversion factor between space and time, the coupling constant in the universe's most fundamental equations.
This number took us 4 centuries to measure accurately. It then revealed that time dilates, space contracts, simultaneity is relative, mass and energy are equivalent, and the universe is woven together in ways no one suspected. One number opened the door to understanding the deepest structure of existence.
That's not just physics. That's philosophy, poetry, and profound truth about the nature of being. The speed of light isn't merely fast. It's fundamental. It's not just a constant. It's a window into the architecture of reality. And we figured it out, against all odds, with our limited senses and evolved brains. We discovered one of the universe's deepest secrets. We measured the speed at which the cosmos operates, understood why it must be that speed, and grasped the consequences that flow from this single fact.
The ancient Greeks wondered whether light traveled instantly or took time. We now know it takes time, and that simple fact, combined with the deeper truth that light's speed is the same for all observers, unlocks the structure of space-time itself. From that foundation, everything else follows. Time dilation, length contraction, E = mc squared, the equivalence of mass and energy, the cosmic speed limit, the light cone structure of causality. It all connects, it all makes sense, it's all true, verified to stunning precision by countless experiments. This is real knowledge about how reality works at the most fundamental level we've yet achieved.
As you finish reading this, take a moment to appreciate what humanity has accomplished. We started not knowing whether light had a speed at all. We ended understanding that light's speed is woven into the fabric of space-time, that it determines how time flows and space extends, that it links mass and energy, that it governs causality itself. This journey from ignorance to understanding took centuries. It required brilliant minds, careful experiments, mathematical innovation, philosophical courage to accept counterintuitive conclusions, and above all, persistent curiosity about how the universe works.